we are given this kind of the stacking of the similar shape, the U shape we have, and we're going to calculate the E. Would that this E be the 3 times of what we get earlier? I don't know, but we can check it out. Okay. So again, this is on your handout. You can dig out your handout and then do the calculation. So for this one, we simply want to calculate the location of the shear center within the value of the E. And so for this case, so right now here for this example, we assume the transverse loading applied vertically. So here this is our neutral axis. Okay, and so the shear flow should be in these directions. Vertical wise, that should be aligned to our loading directions. And then the vertical wise, that must make the continuous shear flow. And so that would be something like this. Okay. So that is the first step to find out the correct shear flow. And then for this case, you can see the we can calculate the shear stress. And basically, the concept is this: on the top here, let me make it equivalent. This will be equivalent to this force, and let me call it F1. And this one will be equivalent to this force. Let me call this is F2. And again, the equivalents are built upon the calculation on the area integral of the shear stress. And then this side, here we make the equivalent force, and let me call whatever the force. Okay, so here, say this one is whatever the F. So the whole thing must be in equilibrium is such that if we would have the transverse loading here, then we know the VE must be in magnitude equal to the contributions of 1, 2, 3, 4, 5 pieces of the forces about the bending, say about this point. Okay, so if we take about this point, then this contribution will become 0, so we can reduce our calculation rigors. Okay, so smartly pick up one point about the bending, say about this point, let me call it C, okay? So then in this way, this will be equal to F1 times A plus 2A, so that means the 3 over 2A plus F2 times A divided by 2, right? So using this kind of equilibrium in bending moment or twisting, then we can calculate E. So that is the strategy here. Okay, so we stick with this one, then we figure out what is the content. And again, here we are given the V, so basically here, the F1 is the integration of the shear stress. So here we put into the two pieces. So for the AB pieces, this is the neutral axis. And then for the other one, DE, this is our neutral axis. So we're simply going to calculate what is the total F1 and F2 in each pieces. So now we can calculate in this way. So for example, say I pick up the shaded area. Okay, so now our formula is tau equal to VQ over IT. And V is our assumed force, and Q. So this is the area will be equal to, let me do this symbolization. So for example here, let me call this is x. So area will be equal to x times, let me call the thickness, this is uniform thickness, let me call the thickness t, okay? And then Q will be equal to area multiplied with from the centroid to here. So that one, here we can calculate this one easily. That one will be equal to, you can see that one, the A is measured from the middle line here. So that one here is how much? 3A over 2, right? Okay, so Q will be equal to area times 3A over 2. And T will be our thickness, our T here. Okay. So therefore, for this calculation, tau will be equal to VQ over IT. V times 2, 3, ATX. And what is I? The I for the whole things, let me calculate here. The I for the entire cross section about the neutral axis, if we follow up these notations, and let me give directly the result, 29 over 4 TAQ. Okay. So here we plug in here 29 for TAQ times T. And this one can be simplified. This one is actually six V 29 A squared T times X. Okay, so that is the function of X. So F1 is the integration of the shear stress on the top portions. So that is from tau 6V 29 A squared T times X. And dA, what is dA? The dA is this one. So basically dA is dx times T. dA equal to T times dx. Okay, so we simply using this formula, T times dx. And integration from this case, that basically integrates from
area,
x
right?
equal to 0, huh?
It's
To
the
A.
area, right? Is it
It's
the
the
integration
area.
of
It's
the
the
area,
area.
like?
Yeah. Integration of the small areas, right? Because right now you can see for this shaded area we are calculating is about the stress at this point, at this segment. So that is the magnitude of the shear stress distributed on the segment. And around that segment we have taken up the small area. So the shear stress multiplied the small area give us a small force. So that small area is dA. Okay. So this one we do the calculations, and this one can be found is 2V. Sorry. 3V 29. Here we don't have any. The t can be cancelled, so t won't enter into this final result, and the a square will be cancelled by the integration of the x. This kind of things. So actually a won't be getting to here. That this is the final form in terms of b. So we can repeat the same thing for the portion D. So for the portion D, then again we pick up the area x like this, and the centroid from here to here is a over 2. So tau